Hello, students. Now I'm going to teach you about the classification of states. It's uh, a subtopic of Markov process. In the Markov process, there will be so many some in TPM you will get some states. So, for example, if we take an example of this one, this is a TPM. Suppose P is equals to suppose this is P is equal. This is the TPM 0.4, 0.6, 0, 0, 1, 0. Here in this case, we can write in the form of P is equals to, and here this is the matrix, and we write the states 0, 1, 2 like this, and here also 0, 1, 2. So in this example 0.4, 0.6, 0.4, 0.6, 0, and next is 0, 0, 1, and 0, 1, 0. So this is the TPM and the states are 0, 1, 2. We need to classify the states. Which type of the state is this one? Okay, we have to find this one. So this TPM can be written in a graphical way, graph way. So we can write like this. This is suppose this is 0 and this is 1 and this is 2. And next here 0 to 0 is possible with the probability 0.4. So self loop. So we write like this with the probability 0.4. And 0 to 1 is also possible. So 0 to 1, I'm drawing an arrow. So with the probability 0.6. And 0 to 2 is not possible. And 1 to 2 is possible. So 1 to 2, I'm drawing an arrow. So 1 to 2, that is the probability with the probability 1. And next 2 to 1. So 2 to 1 is also possible, reverse from here to here with the probability 1. So this is like this, we can draw a graph for the TPM. Next, now I'll explain about all the classification of states. What type of the states? We need to find the states. These are all the many types of states are there. The first one, reachable. Okay. So here, if the probability Pij, what is Pij here in this case? This is P11, P12, P13, P21, P22. Otherwise, we can write like this, P small p, 01. Okay. What is P01? 0 to 1. This is the probability, which is nothing but 0.6. Like this. Pij. I is the state, the left hand side, J is the state, and the top. Okay. Left side is the present values, and top is the top or what? The next values. Okay. Pij power n. This is transition. I'll tell you the transition. So here in this case, uh, P01 power 2, like this, something like this. So I'll write like this, 1 second. And we cannot go 0 to 2 directly. So how can we go 0 to 2 in two transitions? This is first transition. That is in the P power 1 itself, we are able to reach. And 0 to 2 we cannot reach. How do we reach 0 to 2 indirectly? 0 to 1 and 1 to 2. Like this we can reach. That is P01. Actually P02 is the value is 0. And P0 to 2. So we write like this. We write like this. 0 to 1 with the probability 0.6 and 1 to 2 with the probability 1. So the probability of reaching 0 to 2 not in a single transition. So two transitions. That's why we put here like this. Power is not actually power. It's a transition. We say within the brackets we write. That is Pijn is non-zero for some n greater than any number of transitions. Then we say that the state J can be reachable from state I. So J is reachable from, this is suppose in this case, this is J and this is I. So J is reachable from I, but I is not reachable from J because from 2 to 0 we cannot reach. That is 2 to 1 we can move. From 1 to 0 we cannot reach. So I is not reachable from J. See here, I is not reachable from J, but J can be reachable from I in two transitions. This is the two. This is the. So like, so that's the definition of reachability. Here, we can reach 0 to 1 in a single transition. So 1 can be reachable from 0 and 2 can be reachable from 1. So in a single transition. So because transition we got like this. So and next 2 is also reachable from 1 and 1 is reachable from 2. So 1 is reachable from 2. 2 from 2 we can move to 1 like this. So but 0 is not reachable from 2. So from 2 we can move to 1, but from 1 we cannot reachable to 2. So here the probability is from 0 to 1 only, not from 1 to 0. So 0 is not reachable from 2, but 2 can be reachable from 0. So that is called reachability, whether we can move to that state or not, like this. And second state is, second type of state is communicative. What is communicative? If uh, both are reachable, that is 0 to 2 and reachable, 2 to 0 is reachable, then they are communicative. But here in this case 0 and 2 are not communicative because we can reach 0 to 2 but not from 2 to 0. 2 to 0 we cannot reach, 2 to 0 we cannot reach, so they are not communicative. But 1 and 2 can be communicative. 1 and 2 can be communicative because from 1 we can move to 2 and 2 we can move to 1 like this. So we can say another example also, not in a single transition. Okay, in two transitions also. Suppose this is 0 and this is 1 and this is 2. Some TPM, if we get like this and 0 to 1, 1 to 2 with some probability. Probability is not very much important. How much? Whether it is reachable or not, that is important. Probability value is not very much. If the probability is 0, we cannot write that arrow like that. Now, here 0 and 1 can be communicated because 0 to 1 we can reach, 1 to 0 is also we can reach. And 0 and 2 also communicative, not directly, indirectly. So 0 to 1 and 1 to 2. So from 0 to 2 we can reach, and 2 to 0 also, return also we can reach. That is 2 to 0 we can also reach. So 0 and 2 can be reached. 0 can be reachable from 2 and 2 can be reachable from 0. So we say that 0 and 2 are communicative. That is, if I is accessible or reachable, we can say simply accessible or reachable, whatever, from J, and J is reachable from I. This is small I, actually. This is small I. From I. Then we say that I and J are communicative. Here, 0 and 1 communicate to, and 1 and 2 also communicative. In both the ways we can move. 0 and 2 also communicative. But in this case, we can 1 and 2 only communicative. But 0 and 2 are not communicative. And 0 and 1 also not communicative. 0 and 1 also not communicate because 0 can communicate to 1, but 1 cannot give reply. So like this, that's why they are not communicative. So that's it. So that's about communicative. If state I communicates with the state J and J communicate with the state K, then state I can communicate with the state K. Here in this case, in this example, if you see this one, okay. So here in this case, suppose this is I and this is J and this is K. Here in this case, I can communicate with J and J can communicate with K. I can communicate with J and J can communicate with K. Then I can communicate with K. So 0 can communicate with 1 and 1 can communicate with 2. So that 0 can also communicate with 2. That's the point here. Here in this case. So if I is communicates with J and J communicates with K, I to J and J to K, then I to K is possible. That's the thing. And the third thing is essential state. What is an essential state? A state is called an essential state if it communicates with every state. Here in this case, see here, in this example, here there are no essential states because 0 cannot communicate with anyone. So 1 can communicate with the 2 only, but not with the 0. And 2 can communicate with the only 1, but not with the 0. So there are no essential states. A state is called essential state. So if 2 can communicate with both 0 and 1, then 2 is called essential state. If 1 can communicate with 0 to 2, 0 and 2, then that's called essential. But here in this case, in this example, all these are essential states. One second. Okay. Okay. So here in this case, 0 can communicate with 1 and 0 can communicate with 2 also. So 0 can be able to communicate with all other states. So 0 is an essential state. Here in this case, 1 also essential state. 1 can communicate with 0 as well as 2. So 1 is also essential state. Here in this case, 2 is can also communicate with 0 and 1. So all are essential states here in this case. Okay. Next. Next, let us see irreducible. So these are all the types of states. Which state is what type one like this. But irreducible is for Markov chain. So total chain. So we talk about complete TPM. Complete TPM we talk about like this. A chain is said to be irreducible. Total chain is said to be irreducible. If every state can reachable from any state in any number of transitions, any number of transition means 0 cannot communicate with the 2 directly, but in 2 transitions, it can communicate. That is, it can reach. So that's the thing. So in any number of transitions, it is said to be irreducible. Otherwise, the chain is said to be reducible or non-irreducible. So if every state can be reachable from any state, that is essential states. We can say simply, if all are essential state, essential means it talks about only single state. Irreducible means all states. If all the states are essential, here in this case, in this example, 0, 1, and 2, all the 3 states are essential. So this state is irreducible. It is irreducible. Irreducible Markov chain. Okay, so we say that. And next thing is absorbing state. Irreducible is about complete chain. But here in this case, absorbing state is about only single state. So in absorbing state means in any example, suppose P is equals to, so I'm taking 3 states, we can take 2 or 3, 4, 5, any number of states. But here if we get some 0, 0 and 0, 0.2, I'm taking some example randomly, I'm taking 0, 0.5 and 0.5, something like this. Okay. If you see like this, main principal diagonal, if we get 1, then the state is absorbing state 0, 1, 2, and here also 0, 1, 2, like this. So here 0 is the absorbing state. So in principal diagonal, if we get 1, that is simply we say that Pii is equals to 1. That can be 1, 1, 2, 2, 3, 3, whatever. P1, 1, P2, 2, P3, 3. If we get 1, then that state is called absorbing state. Okay. A state I is said to be absorbing state if and only if Pii is equals to 1. In the principal diagonal, if we get 1, that's called principal, what do you call, absorbing state. Okay. And next, observing state is over. Next, we shall see periodic state. This is very important. Important things are irreducible is important, and periodic and aperiodic are very, very important. And transient and recurrent ergodic. Ergod is also very important. Now let us see the remaining. The periodic states. What is the meaning of periodic states? Let us see. A state is said to be periodic with the period t greater than 1, always t greater than 1 period if the return to the state is possible only in t, t2t, and 3t steps, where t is the greatest integer with the property. So I'll explain simply. If t is equals to 1, we say that it is aperiodic. Opposite of periodic is aperiodic state. The state is said to be aperiodic if there is no t exists. Suppose t is equals to 1, simply we say that that is aperiodic. Okay. Now in the previous examples, I'll explain using the previous examples. Okay. Now, so Aperiodic means we have to start with the state. So with to find the periodicity of the state, we have to start from zero. Again, we have to return back to zero. In how many steps like this we have to say? Okay. So in this case, we see the simply I'll say GCD, greatest common divisor, simply. Okay. So 0 to 0 we can reach. So how many transitions? One. Okay. And 0 to 0 we can reach in another way. So we have to find all the paths starting from 0 and we have to return back to 0. All the paths. First path is 0 to 0. Second path is there is no second path because if we move to 0 to 1, we cannot return back to 0 again. So only GCD of 1 is 1. So we say that this is a periodic state. This is a periodic state. And next, let us see about the one. So we have to see all the paths. Okay. Now, GCD of, I'm checking the periodicity of state one. From one, we cannot go to zero, but we can move to two and return back. In how many state transitions? Two. We have to return back. Wherever we start, you have to return back. We have to find all such paths. Okay. Is there any other path? So it seems to be there is no path, but there is a path. We can move from 1 to 2, 2 to 1, again 1 to 2, and 2 to 1. So two times we can traverse. That is 4. Like this, we can get 6, 7, 6, 8, something like this. So GCD of 2, 4, 6, all these things is 2. So 1 is the periodicity with the period t is equals to 2. So here in this case, t is equal to 2. We can return back in 2t, that is t, 2t, 3t, something like this. So here in this case, t is equals to 2. So in two transitions are 4, 6 like this. We can move 2, 4, 6 like this. We have to find all the GCD. So a state is said to be periodic with the period t is greater than, always greater than 1. If it is equal to 1, that is aperiodic. If the return to the state, we have to start from that state and we have to return back to the state. We have to find all such paths to the state is possible only in t, 2t, 3t, and here in this case, so we can find t is equal to 2, 4, 2, 4, 6, 8. So we can 6 also possible. So 1 to 2, 2 to 1, 1, 1 to 2, and 2 to 1, 2, and 1 to 2, 2 to 1. 6 states also we can find. So like this, we can find it. So that's why it is called periodic state. One is periodic state and zero is not a periodic. If we say that it is a periodic. Now let us check with about two also. Here I'll write uh, GCD of GCD of 2. What is GCD of 2? So here in this case, 2 to 0 is not possible. So we can move to 2 to 1, 1 to 2. How many transitions? 2. Same way as 1, we can also, 4 is also possible here. So what is that one? 2 to 1, 1 to 2, and again 2 to 1, 1 to 2. So four transitions. So 2, 4, 6, 8, something less. We get all these things. GCD of this one is 2. So here also, this 2 is also a periodic state with the period t is equals to 2. Like this, we have to return back to the state. Like this. And here in this case, here also we shall see. I'll take eraser. No. Here I'll find the periodicity of all these states. Okay. Periodicity of this one. So first, to find the periodicity, we write a GCD of. I'm finding the periodicity of 0. So 0 to 1 and 1 to 0. We can move. So how many transitions? 2. And 0 to 1, 1 to 2, 2 to 1, and 1 to 0 is also possible. That is in how many? 4. We can also find 6 also. 0 to 1, 1 to 2, 2 to 1, again 1 to 2, and 2 to 1, and 1 to 0. That is nothing but 6. 6, 6, 8. Like this, 8 also we can find. 0 to 1, 1 to 2, 2, 1, 0 to 1, 1 to 0, 0 to 1, 1 to 0. Like this, we can find all even numbers. So we can say simply, and so on. We can find 2 or 3, something like this. So GCD is 2. So 0 is a periodic state with a period 2. And what about 1? So let us find periodicity of 1. So 0 to 1, 1 to 2, possible. So 2. And from right side also, 1 to 2, 2 to 1. So only 2. So we write only one time. And here in this case, 1 to 2, 2 to 1, again 1 to 2, 2 to 1. Like this also right side, 1 to 0, 0 to 1, 1 to 0, 0 to 1. So 4 transitions also we can possible. 6 also possible. So 1 to 0, 0 to 1, 1 to 2, 2 to 1. Here we got only 4. Okay, again 1 to, again 1 to 0, 0 to 1, 6. Like this, we can find 6. So we get in any transit, we get only even number. So 2, 4. Here also periodicity 2. And 2 also we get 0 to 1, 1 to 2, 2. And 4 also possible. Well, sorry, 2 to 1, 1 to 0, 0 to 1, 1 to 2. That is 4. 2, 4, 6. Here also same thing. So these are all these states are periodic states with the period 2. All these are with the period 2. So here in this case, in these two examples, 0 is a periodic state, that is only 1. And next, 1 and 2 are periodic states with the period 2. Okay. And here in this case, once I'll add one thing, 0 to 0. I'm writing self loop. Then it becomes aperiodic. Whenever any state is self loop, that is aperiodic. No need to check it again. So if you observe the thing, so I'll see here, I'm writing self loop for this one. Okay, self loop. So now let us again find GCD. So how is it possible? 0 to 0, 1 transitions, 1, comma, again 0 to 1, 1 to 0. That is 2. 3 is also possible if you observe. 0 to 1, 1 to 0, 2 over 0 to 0, 3. 3 also possible, and so on. So like this, we get GCD is 1. If since the GCD is 1, we say that 0 is a periodic state. So we could simply say that it is a periodic state. So that's why simply whenever there is a self loop, then that's definitely a periodic state. Simply we can say. Okay. A state is said to be a periodic with the period di where di is greater than 1. Aperiodic if di is equals to 1. Here in this case, di is the GCD. So here it's not given GCD, but I'm telling in the some way. Okay. So next step. Let us see the very important. Another important is transient states. Okay, transient states. Okay, I'll write it again. Transient states. Okay. Uh, A state I is a transient state if there exists J which is reachable from I. Here also this is small I, but the state I is not reachable from state J. So I have to take the first example only. So see here 0, which is a self loop. So whenever there is a self loop, you directly say that it is periodic. 1 and 2. This is first example. Again, I'm writing 0 to 1 is possible. 1 to 2 as well as 2 to 1 is also possible. Okay, with some probabilities. Probabilities are not important. If the probability is greater than 1, that's it. Okay. And here in this case, let us find what is this transient state. If there exists state J, which is reachable from I, but I is not reachable from J, then 0 is called, then I is called transient state. Here 0 is the transient state. That's the meaning. If there exists J, a state J. Here in this case, state J is 2. I'm taking example 2, which is reachable from I. 2 is reachable from I. That is, I is nothing but 0. So 2 is reachable from 0. From 0, we can move to 1, 1 to 2. So in 2 transitions, we can reach. But the state J, that is 0, is not reachable from J, that is 2. So 0 cannot reach from 2. From 2, we cannot reach. 2 to 1 we can move. From 1 to 0 we cannot move. So 0 is not reachable from 2. So 0 is called transient state. That is, we can travel from 0, but we cannot return back. That's a transient state. Got it? We can travel from 0 to outside, but we cannot return back. Then that the state is called transient state. Here, 1 and 2 are not transient. So here in this case, the states which are not transient are called recurrent state. Recurrent state. If a state is not transient, then it is called recurrent state. Then that is called a recurrent state. So 1 and 2 are called recurrent states. These two are recurrent. 1 and 2 are recurrent. Why? Because there are no states J which is reachable from I and we cannot return back. So from 1 we can move to 2 as well as we can return back. So from 1 we cannot move to anywhere. So 2 also we can move to 1 and return back. If we can return back, that's called return recurrent. If we can return back, that is called recurrent. If we cannot return back, that's called transient. We can travel but not return. From 0 we can travel to 1 or 2, but we cannot return back. So that's why it is called transient. But 1 we can move to 2 as well as we can return back. 1 to 0 is not possible. So I'm not checking that one. Okay, we have to check all the states like this. So if we can travel but cannot return, that's called transient. We can return back. If we can return back, that's called recurrent states. That's a very important thing. And ergodic, actually, it's not ergodic state, ergodic chain. It's about ergodic chain, not state. Here in this case, all are classification of states except this irreducible. Irreducible is about chain as well as ergodic is also about chain, complete TPM. We talk about complete chain or TPM. From TPM only we get this chain. Okay. So simply, what is ergodic? Only two things. All the states must be aperiodic. AR, just simply AR. All the states are aperiodic. That is periodic with one. Periodicity one. If all the states have periodicity one, that's called aperiodic. A as well as recurrent. If all the states are recurrent, then that's called ergodic. In this case, one is aperiodic, but 1 and 2 are not aperiodic. Here, these two with the periodicity is 2. That's why it's not ergodic chain. It's not ergodic chain. So aperiodic as well as recurrent. Here in this case, 1 and 2 are recurrent. But what about 0? It's a transient. If all the states are recurrent, then that is called ergodic. So we have to check all these things. So it's not recurrent also. This chain is not recurrent as well as it's not only 0 is aperiodic. 1 and 2 are not aperiodic. So that's the thing. Here in this example, if you see, all are periodic. So because all the periodicity is 2 only. 0 periodicity is 2 and 1 is periodicity 2 and 2 is also periodicity 2. It's not also ergodic. So all the states periodicity must be 1. So then only we say that aperiodic. But all are recurrent. Here in this case, all are recurrent but not aperiodic. 0 is recurrent. We can return back. 1 can be recurrent. We can return back. From 1 to 0, we can move and as well as we can return back. And 1 to 2, we can return back. So that's why if we can return back, that's called recurrent. All are recurrent, no problem. But what about periodicity? Periodicity is 2. So they are not aperiodic. So it's also not ergodic. It's also not ergodic. Okay, I'll tell you some ergodic. So we have to check both the rules, aperiodic as well as recurrent. All the states are recurrent as well as all the states are aperiodic. That's called ergodic states. If all the states in the chain are aperiodic as well as recurrent. So we have to remember these two, aperiodic as well as recurrent. Then the chain is said to be ergodic chain. All the states must be aperiodic as well as recurrent. In this example, both the rules fail. That is, all are not aperiodic. Only 0 is aperiodic. And 1 and 2 are not aperiodic. 0's periodicity is 1. 1 and 2 periodicity is 2. So Only 0 is aperiodic. These two are not aperiodic. All the states must be aperiodic for ergodic, and they are not recurrent. But here all are recurrent but not periodic, aperiodic, but not aperiodic. Okay. So, uh, and this is about classification of states. This much is very important for you to understand all the classification. In next example, in the next video, I will take some problems and explain about all these reachability and communicative, all this. So let us take problems in the next class.